Before we get into the student notes, let's go ahead and take a look at a little preview by finding the population mean. The mean, also known as the arithmetic average, is found by adding all of the data values in a data set, then dividing by the total number of values. If the data for which we are to calculate a mean is gathered using all members of a population, then that mean would be called a population mean. Measures calculated using population data sets are called parameters. The calculation of the mean is carried out by adding all of the data values in the data set and dividing by the number of data values as mentioned before. Here is the formula. The Greek symbol mu stands for the population mean. The Greek symbol sigma stands for summation, meaning adding all the values up. The letter X represents the values of the variable, and these values are the data values in the data set. The uppercase N represents the number of data values in the population data itself. The first thing you will do in this formula is add up all the values that are in the data set. Once all those values are added up, you will then divide by how many data values there are. The table below shows the ages of all 100 members of the 114th United States Senate as of June 2016. Since this data represents the data for all of the members of this population, a mean calculated from this data set would be a population mean. The formula tells us to add all the data values, then divide by the number of data values, in this case 100. So we will add 76 plus 48 plus 54 and continue this process until we get to the last entry in the table. Then we will divide by 100, which is the number of values in the set. As you can see, we're adding up all the values in the table. The dot 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 here in the middle just represents all of the data values I was not able to fit into the screen. After adding all those 100 data values up, then dividing by 100, we get 62.65 years. An important note is the rounding rule. And the rounding rule for the mean tells us to round to one more decimal place than occurs in the raw data. Since all of the numbers in the data set are whole numbers, notice here that my average we round to the 10th place. So in this particular case, our average would be rounded to 62.7 years. Again, the mean, also known as arithmetic average, is found by adding all the data values in a data set, then dividing by the total number of data. If the data for which we are able to calculate a mean are gathered using a subset or a sample of the members, then this will be called a sample mean. So notice here, we're not adding up all of the data, just a subset or a sample of the data. Measures that are calculated using the sample data sets are called statistics. The actual steps for calculating a mean are the same, whether we are using a population or sample mean. The formula is as follows. It looks very similar to a population mean with some slight differences. Here again, the similarities are the Greek symbol sigma, which means summation, meaning we add up all the data values in the sample set. The X represents values of the actual variable itself. These are the actual data values in the data set. And lowercase n represents the number of data values in the data set. Again, all very similar. As another example, in the year 2016, there were 435 members of the United States House of Representatives. This table below shows a random sample of the 435 members. Now, trying to find the sample mean is a lot easier. So instead of trying to find the mean of all 435 members, we're just looking for a sample mean of just 30 of them, preferably randomly selected from the House of Representatives. This data set represents a sample of the population, so we are going to calculate the sample mean. Again, it's the same calculation as that for population mean, but the difference is in the notation only. Let's add up all the data values, then divide by the total number of values, in this case 30. So again, the dot 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 here represents the numbers I could not fit on the screen, but I essentially added up all the numbers that were on the previous table in the previous slide. Here you'll notice we got 61.9 years. Again, since the data values that were given to us are whole numbers, we round to the 10th place. Now there is a problem with sample mean, and that's called sampling error. The mean age for the sample of 30 members of the House of Representatives is 61.9. However, if we were to go ahead and find the mean for all 435 members, we would see that the actual population mean is 57 years old. So clearly, we're not in agreement here fully. Maybe it's close, but it's not quite right. But the purpose of gathering sample data and calculating sample statistics is to estimate population parameters. Sometimes, gathering all of the population data is unattainable, and gathering estimations is best. But because of sampling error, these sample statistics will sometimes be good, but other times be poor estimates. The sample mean of 61.9 years for the random sample ages of members from the House of Representatives appears to be a poor estimate of the actual population mean of 57 years old. The techniques of inferential statistics will show statisticians to judge the quality of an estimate and make improvements to those estimates, but these techniques we'll study at a later time. Mean for grouped data. In a previous PowerPoint, we used the data for the number of electoral votes for each of the United States to construct a grouped frequency distribution. However, without access to the raw data values, it is impossible to calculate the exact value of the mean for the dataset. However, it is possible to approximate the mean for a dataset that has been summarized in a group frequency distribution. The procedure for finding the mean for grouped data assumes that the mean of all the raw data values in each class is equal to the midpoint of the class. The class midpoints are used as reliable approximations, since some values fall above the midpoint and others fall below. A way to construct a grouped frequency distribution is as follows. First, start with our table. Note the limits and the boundaries along with our frequency. These numbers should look familiar as we have done this example in the past. But not only do I want to set up the class limits and the frequency, I also want to set up what are known as midpoints. Our midpoints are simply going to be the lower bound plus the upper bound divided by 2. So notice my first midpoint is 6.5, which obviously 6.5 is smack dab in between 3 and 10. 14.5, smack dab in between 11 and 18. And then what we do next is very important with regards to grouped frequency data. What we're going to do is we're going to take the midpoint and multiply it times the frequency in each row. Notice our first row we get 221. That's 6.5 times 34. The next row is 11 times 14.5 gives us 159.5, and so on down the list. Each of the entries in the last column represents an estimate for the total of the data values that fall in each class. Now we're going to find the sum of the values in the last column. Go ahead and add all these values up here, and they should lead us to 579.5. Next, we are going to divide the sum of the products of the frequencies and the midpoints by the sum of the frequencies, which is the size of the data set n. The formula looks like this. Simply put, we take the 579.5 from the previous slide, divided by the fact that we have 51 data values, and we end up with 11.4. Once again, since we have whole numbers as our data values, we make sure that we go ahead and round by one more decimal place than those whole numbers, which will be the tens place. And we estimate that the mean number of electoral college members per state is 11.4. Now, in reality, the actual mean number of members per state is 10.5. Our estimate was 11.4. The discrepancy occurs because, in the absence of the raw data, the individual data values for each class were estimated using midpoints of each class. Weighted mean. A philatelist has 200 stamps in his collection. A distribution of the valuation of the stamps is shown in the table to the right. He has 60 stamps, each valued at $20. He has 45, each valued at $15, and so on. To calculate the mean value for each stamp, we would need to add the value of each and every stamp, all 200, then divide by 200. But to do this, we would have to add 20 60 times, then add 15 45 times, and continue on until we have added the value of each stamp down to the 5 stamps valued at $4 each. But this is a lot of work. Instead, if we think about this for a second, we can go ahead and just simply multiply 60 times 20, then add that to the product of 15 times 45, and continuing this process down to 5 times 4, then again dividing by 200. Following this route will give us the same answer at the same time with a lot less work, and it's called the weighted mean. Now, you can't do this for every example, but you can do it when you notice there are repeated data values. The weighted mean is used when the values in the dataset are not equally represented. The formula for the weighted mean is to multiply the weight of each data value by its corresponding value, then add those products. Then after that, divide by the sum of the weights. But first, we must determine what are the weights and what are the data values. We are finding the mean value of each stamp in the collection. So assign the variable x to the dollar values, and the weights then will be the number of stamps at each value. We will multiply each dollar value by its corresponding weight, then add them up. Then divide that sum by the sum of those weights. This gives us a total dollar value of $2,590. Then divide the total by 200 stamps. Thus, the average value of the stamps in the collection is $12.95. Now let us follow along with our student notes. Make sure you ask any questions and let me know if you have any. Now it's time to follow along with your student notes. Measures of central tendency are also called averages. Notice the purpose of each and how to use them and describe the data accordingly. First, let's review. Population. Population are all subjects of interest or being studied. Subjects may be humans, animals, business entities, products, etc. The size of the population usually makes gathering data from every subject very difficult, if not impossible, due to expense or time. The preferred way of gathering data is through a sample. In other words, a group of some subjects related to the population. Any measures found by using all data is known as a parameter. Measures found by using data values from a sample are known as statistics. In statistics, round only after the final answer is calculated. Intermediate rounding is generally bad, which increases the difference between the answer and the exact value of the statistic. Try to round at the very end. The mean is the arithmetic average, found by adding the values of the data and dividing by the total number of values. It would be a good idea to round the calculated value of the mean to one more decimal than occurs in the raw data. The population mean, denoted by the Greek symbol mu, is calculated by using all values in the population. The population mean is called a parameter. Here is the formula. Notice that in the top, I'm adding all data values, denoted by sigma, and in the bottom, we're dividing by the total number of data values. X represents the data value in the population, and capital N represents the total number of values in the population. The sample mean, denoted by X bar, is calculated using the data values in a sample. The sample mean is known as a statistic. You'll notice that the formula looks very similar to the population mean. The difference here is that there are much less data values than that of the population, making it easier to calculate. Again, X represents the data value in the sample, and lowercase n represents the total number of values in the sample. As a side note, Greek letters tend to denote parameters, and Roman letters denote statistics. Let us assume that the data are obtained from samples unless otherwise specified. Below is a very familiar example. The salaries are of a sample of 30 college and university coaches in the United States. Let's find the sample mean. Once again, we simply add up all these values, divide by 30, and we end up with 346.8. I invite you to pause the video here, add up all these values you see, divide by 30, and make sure you get the same value as I do. In the previous chapter, we constructed a frequency chart with 8 classes for this sample. Let's use the frequency chart to calculate the mean for group data. This process is most frequently used when the raw data is not available. Here's the formula, where f is the frequency, x sub m is the midpoint, and of course lowercase n is the total number of data values. Let's calculate the mean for group data. First, we take the frequency and multiply it by class midpoint. In the first row, we can see we get 2029.5. 5 times 274.5 gives us 1,372.5. And on down the list we go. Adding up every single one of these values here gives us 10,395. So to calculate the mean for group data, we go ahead and take that total, 10,395, divided by 30, the number of coaches in this case, and we get 346.5. Now comparing the sample mean calculated from raw sample data to that of the group data mean in the frequency chart. Compare sample means calculated from the raw sample data and from the grouped data we just saw in the previous slide. And note that the mean in most cases is not an actual data value. So as a review, the properties of the mean are as follows. First, the mean is found by using all values of the data set, whether it be population or sample. And unless told otherwise, we usually assume it's a sample set. 2. The mean of a data set is used to compute other statistics, such as standard deviation, as we will learn in future lessons. 3. The mean of a data set is not necessarily one of the data values. 4. To find the mean of a frequency distribution, there must not be an open-ended class. And 5. The mean is affected by extremely high or extremely low values called outliers. The median is the center or middle of an ordered list of data. The symbol for median is MD or MED. To find the median, first arrange the data from smallest to largest. In many cases, please use your TI-84. 2. Determine what number of values n are in the data set. If n is odd, then the middle data value is the median. Or, if n is even, the median is the mean of the middle two values, meaning you'll add those two values up, then divide by 2. Let's do an example. Here, our data value is already in order from least to greatest. What is the median of this data set? Well, we'll notice that we have 36 salad dressings, which means we have an even number of data value. So if we go ahead and count these up, half of 36 is 18. That'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 is in the middle, along with 19. The 18th and 19th values are the middle two values of this even-numbered set of values. So we simply add those up, get 260, divide by 2, and we're back at 130. The NOAA reports the number of tornadoes per year. Here is a list of number of tornadoes per year for the last 7 years. First, we put these numbers in numerical order, from smallest to greatest. Now that we have them in numerical order, we see which number is the middle. That will be our median. As you can see, we have 3 numbers to the left, 3 numbers to the right, making 1156 our median. Now let us review some properties of the median. The median is used when one needs to determine if a data value falls in the upper half or lower half of the distribution. The median is not affected very much by outliers, as opposed to the mean. The median can be used with open-ended distributions. Now we talk about the mode. The mode is the value in the dataset that occurs most often. Datasets that have only one value that has the greatest frequency are called unimodal. Let's do an example. Let's find the mode of the following set. There is one mode in this particular example. You'll notice that 10 repeats 3 times. Since 10 is the only number that repeats with the greatest frequency, it has again one mode. Therefore, this sample is unimodal. Datasets that have exactly 2 values that occur with the same greatest frequency are said to be bimodal. Let's go ahead and find the 2 modes that are in the following bimodal dataset. We see here that 104 repeats 1, 2, 3, 4, 5 times. So far, this looks like it's a unimodal set because that repeats 5 times. However, you notice that 109 also repeats itself 5 times. Since they both repeat at the greatest frequency of 5 times, and that no other data value occurs more than 5, 104 and 109 are the modes. In a previous example, there were 3 values that occurred 6 times, which is the greatest frequency, which means this dataset is multimodal. Again, notice here, 120 repeats 6 times, 130 repeats 6 times, and 160 also repeats 6 times. Some datasets have no mode at all. This happens when all of the values occur at the same frequency. In a previous example, we had no mode, where we noticed that each number occurs exactly 1 time. This is an example of no mode. The mode is the only measure of central tendency that can be used to find the most typical case for nominal data. In this example, we have nominal data of the worldwide sales in billions of dollars for fast food franchises for a specific year. The category with the greatest frequency is KFC. Thus, the most typical case has sales of 14.2, meaning the mode is KFC. Let's review some properties of the mode. The mode is used to find the most typical case. The mode is the easiest average to find. The mode can be used for qualitative and quantitative variables. The mode is not necessarily unique and may not even exist. Now, there are some measures that are resistant. And a measure that is resistant is when an extremely high or low data value does not change the value of that measure. The median and mode are resistant. However, extreme values, called outliers, have a striking effect on the mean. And we will learn how to determine which values are outliers later on. The following dataset has a value that is much higher than the rest. In particular, I'm speaking of the number 240. Now, one might think, well, 240 is not that far away from 189 or 177. But it is far away from 189 and 177 when you consider the fact that all the other data range from 120 to about 190. If we were to remove that 240 from the list, we get the following set. Notice again that my list of data values does not include 240. What I would like us to do is go ahead and find the measures of central tendency, then compare and contrast the values. This here is the original. This here is the edited data set. So the measures of central tendency for the first data set are as follows. There is no mode, the median is 157, and the mean is 164.6. Calculating each one of these measures should be fairly simple. I invite you to pause the video here and verify that these three are the case. However, let's go ahead and remove the 240, and let's go ahead and calculate the mode, median, and mean again. Without the 240 included, we see that there is still no mode. The median is still 156. However, the median goes down to 157. Once again, you'll notice that the mode stays the same. It's resistant. The median changed slightly, which means it also is resistant. However, you'll notice that the mean changed drastically. Here's an example of how mode and median are resistant, but mean is not. Mean has a striking difference from the previous list to the edited list without the outlier. So again, notice how much the mean changed and how close the median stayed the same and the mode stayed exactly the same. Now, mid-range. The mid-range is the arithmetic mean of the lowest and highest values in the dataset. It is the midpoint of the range. It is not efficient nor resistant. However, it can estimate the center for uniform distributions. The formula for midrange is as follows. The highest value plus the lowest value, all divided by 2. So let's find the midrange of the previous set data. So this is a repeat from the previous example. And let's find the midrange for both. The original data set gives us a midrange of 122 plus 240 divided by 2, which results in a midrange of 181. Now let's go ahead and find the midrange for the data set after deleting the extreme value of 240. That would be 122 plus 189 divided by 2, which gives us 155.5. Is it reasonable to use the midrange as a descriptive statistic for this data set? Now, it could be used as a descriptive statistic for the edited data set since the values are fairly close to the median. Notice again, this value is fairly close to the median from the previous slide, and therefore, yes, we can use it as a descriptive statistic. Let us review some properties of the midrange. First of all, the midrange is easy to compute. Second, the midrange gives the mean of the range of the data set. Notice this is not the mean, but is the mean of the range. Again, lowest plus highest, all divided by 2. Now, the midrange is affected by outliers, as seen from the previous example. Now we will look at shapes of distributions. In the future, we're going to see how these shapes are also going to be significant, but for now, we're just going to start with the basics. The 3 most important shapes to consider at this point are positively skewed, symmetric, and negatively skewed. Now, we've talked about this before, but let's go into a little bit more detail here. For positively skewed or right skewed distributions, most of the data falls to the left of the mean and clusters at the lower end of the distribution. Notice again, for a positively skewed or right skewed distribution, here's my mean, and most of the data falls to the left. The tail stretches out to the right. Notice how this tail is off to the right. And that really is why it's called right skewed, by the way. The mean will be to the right of the median, and the mode will be on the left of the median. The mean is also pulled toward the tail by more extreme values. So the more extreme values we have over on this end, the more the mean will be pulled to the right. For negatively skewed or left skewed distributions, you'll find a similar result. Simply changing left and right, we end up getting the most of the data falls to the right of the mean. Again, notice that you have the mean here. Most of our data is this way, as indicated by the tall vertical bars. The tail stretches to the left as it tails off. The mean will be to the left of the median, and the mode will be to the right of the median. And finally, the mean is pulled towards the tail with more extreme values. Symmetric distributions. The data values are distributed evenly on both sides of the mean. The distribution is unimodal. In other words, the mean equals the mode equals the median. Notice they all line up here. And on top of that, they are at the center of the distribution.